The following visualization shows you what will happen if you put the dielectric slab between two different parallel plates. One of them is using constant charge and the other is using constant voltage. So as you can see here, the forces are different, but they both attract. And so by the end of this video, you will be able to understand why this happens by understanding the electrostatic energy as well as the capacitor. So before we get started, please check the notes in the description for the notes throughout this entire discussion, as well as the timestamps for you to skip through just in case if you only want to understand a certain topic. So before going to the full deep dive into the physics, we should understand first about work. So work is defined to be the integral of f dx, from your initial position to your final position. So let's say if you have a particle going from point A to point B, and you're asking how much work did my force do. So let's say if you want to figure out the work by the electric field, you just substitute the force here to be the Q times E vector, which is the electrostatic force. And substituting them in, this would be Q to the integral of A to B of E vector dx. And E vector is defined to be negative gradient of phi, where phi is the scalar potential. So if you try to plug it in and also evaluate the integral, this would be negative q times phi b minus phi a. So there's an electric field from here to here, from high to low. And so there will be a force going in this direction because this is the electric field, and with positive q. And what you see here is that the result of this work here is positive. When it is positive, this would mean that your force is aligned towards your trajectory. But notice something here. If you apply a force towards your particle, this would mean that your particle would accelerate. And normally, you wouldn't try to consider when the particle is accelerating. So you might try to make sure that the velocity is quite constant. And the way that you do this is by adding another force. This is the force by the external field, just to make sure that the sum of the force will be zero. So you could ask what is the work by the external field, and this would be the integral from A to B of the F external dx. And this is basically just the negative of our previous equation. This is going to be Q phi B minus phi A. And this is less than zero, meaning that this work is trying to go against the trajectory. So another way to visualize this is that if you have a high UA and a low UB, and then the energy will drop. You can see here the potential energy drop, meaning that there should be another energy that is contributing towards the system. And it turns out that this is the work by the externals. So instead what you're doing is that you are trying to extract work from your system. So that's everything that you need to know in order to get started with the electrostatic energy. So before we continue on, please consider liking and subscribing, since I will be posting more discussions on physics. So now let's consider about the potential energy. So in here we'll be discussing about a group of point charge. So let's write this down. Group of point charge. So the problem is quite simple. Let's say if you have a system in which you have already configured point charges to be at certain locations. The question is, how would you define the potential energy? And the way that you do this is actually quite simple. So let's just first try to move one particle from infinity towards your location. And this will be work 1. So work 1 in here would be actually 0 because there's no electrostatic potential inside here, and on the outside, because it's very far, you could consider that the electrostatic potential is just 0. So you have already managed to put one particle in, and it is charged. Second of all, you would try to move another particle in, and let's say it has a charge Q2. This would have charge Q1, and the end goal is to have it within a distance of R12. So if you refer to the formula here, the work from the external, in order to move from one point to the other, this would be, for the work 2, this would be Q2, multiply this by phi b, the final point minus the initial point. The initial point is 0, and the final point, you could just use the formula for the electrostatic potential for point charges, which is 1 over 4 pi epsilon 0 times Q1 over R12, like so. And so simplifying this would be Q1 Q2 over 4 pi epsilon 0 R12. So you could also do this for the third charge. This would be Q3 times, and so if you put the third charge in, you need to consider both from Q1 as well as from Q2. So you just need to sum them both up. This would become Q1 over 4 pi epsilon 0 R13 plus Q2 over 4 pi epsilon 0 R23, like so. So if you sum up all of the works here, this would become your potential energy. So this is the amount of work that is applied in, which is going to increase the potential energy. So the sum of the WJs, and so the WJ here, if you look at the pattern, this would be the sum of J equals to 1 until N, the sum of K equals to 1 until J minus 1 of Qj Qk over 4 pi epsilon 0 Rjk. Now if you notice here, this could be denoted as a matrix. So you could have a J by K, and you're basically only summing this certain part here. So the one at the lower triangle, like so. But if you look at the WJK again, WJK is the same thing as the WKJ, meaning that you could actually just sum something like this. You could just sum this up as well, and then later divide it by 2. So we can write it. It will be the sum from j equals to 1 until n of the sum of k equals to 1 until n of half wjk. But if we only write it like this, what if j is 1 and k is 1, or w11? W11 here would mean that you would need to have R11, which is going to be 0. And this will later going to be blowing up your potential energy. So this doesn't make sense. So instead of defining Wjk to be fully like this, we will also define Wjj to be 0, so that this equation will be fulfilled. Another way to write this down is by actually denoting a prime at the top. So denoting this prime at the top means that you would sum them all up except when j is k. So you are only summing them up only when j is not equal to k. And also you could simplify this much more further by noticing that you could just bring the half towards the front, sum of j equals to 1 until n, and then there's the qj, which could be brought out because this is not a function of j. So it will be qj times the sum of k equals to 1 until n of the prime of qk over 4 pi epsilon 0 rjk. Now this thing here at the bottom, at this right side here, we call this to be the electrostatic potential phi j. So therefore, this is simplified to be the sum of n of j equals to 1 of qj times phi j. So why is there a difference between this potential energy as well as the work? The answer actually comes from how we actually define the system. So for the first example, we have a constant electric field and you have a charge. When the charge is moving, this would change its potential energy because this electric field is still constant, so it's still just a q phi. But if you consider, let's say, two different particles and you try to move from one place to the other, this is going to be increasing its potential energy. But also, if you look at it from this other particle, it's also going to be increasing its potential energy, meaning that you're double counting it. So therefore, you need to divide it by 2 in order to get your actual potential energy. You don't create energy out of nothing. So that was the potential energy for a point charge. But let's consider something much more better. Let's consider the potential energy, but instead we'll be considering for a charge distribution. Charge distribution. So if you have, let's say, a potential, and then you try to add in small charges q that it doesn't change the phi prime here, this is basically your work, your small work basically. Now instead of considering a point charges, we'll consider the charge distribution, which means that it will have the sigmas over the area, as well as the volumes over the volume. Now because we are considering the very final state to be a certain charge distribution, we could just denote the current charge distribution, let's call that rho prime, to be alpha times rho. where rho is the very final state. So that means that for a very small change, the d rho prime would basically be rho times d alpha. So therefore, we could rewrite this. The work would be the integral of the d alpha times the integral of the phi prime of rho dv plus phi prime sigma dA. Well, this is the volume, sorry, the surface, and this one's the volume. This is from 0 to 1. Because the very final state, the alpha should be 1, and for the very initial state, it is where there's no charges, or when the charge is 0. Now, you should also notice that phi prime actually depends on the charge distribution, and it's actually proportional. Therefore, we could just express phi prime to be alpha times the very final phi. And so if you do the integral, it's going to be half times the integral of phi prime, sorry, it's phi times rho dv plus the sum of the surfaces of the phi times sigma dA, like so. And you could also define what phi is. So the scalar potential, if you already know, this is just 1 over 4 pi epsilon 0 of the integral of the volume rho over r minus r prime, this is position r prime, dv, plus the sum of the surface, same thing, r minus r prime of sigma r prime dA. So now this expression is the general case. And you could actually try to consider if, let's say, you have a conductor within your system. So for a conductor, the rho is 0, but there could be sigma, but the phi is constant. So the potential energy here, the U, would be half times the integral of the sigma, no, the integral of the surface of phi times sigma dA, or this is just half q phi. Q phi. And this is only for one conductor. If you have multiple of these conductors, you would just need to sum them up with respect to I, like so. So the much more general case would be when U is the integral half times the integral of the volume of rho phi dV for the dielectric, like so, plus the sum of the surface sigma phi dA for the dielectric, plus q phi for each of the conductor, like so. So notice the difference here. At the bottom, you see that there's this q phi, which is also represented in here. But at the bottom here, there is also this rho phi as well as the sigma phi. And this corresponds to the self-energy when you put it when you try to implement a charge distribution. But anyways, you could also prove this by assuming that the point charge is very small, such that there are infinitesimal charges that you could just put this up into something like this, in which there's the charge density and the scalar potential. So that's the potential energy for a charge distribution. And so we could actually extend this much more further into the idea of storing the potential energy in the electric field. And alongside that, we'll also be discussing about the energy density. In here, this is the energy density from the electrostatic field. So to convert this potential energy into this energy density, we first need to use some Maxwell's equation. First is rho is the divergence of the displacement vector, and this is applied for the dielectric, because for the conductor this would be 0. And also sigma would be the d vector dot n hat, and this is within the conductor surface. So if you actually look at a system, let's say something like this, and you have some of the dielectric field, right? So you could just define a conductor, and there will be a surface here, and the normal vector would be going outside like so, and this entire thing would be the volume except for the one at the center there. So by using the general case, the potential energy would be half times the integral of the volume rho phi dV plus the integral of the surface rho sigma dA, like so. Now we can substitute your values, and here the surface is going to be this conductor. So therefore, we can rewrite this as the d vector dot n hat, and for the rho, this would be the divergence of d vector. And so this could be rewritten as half times the integral of the volume, but in here I'll be doing something that's slightly different. Instead, we'll write this as divergence of phi d vector minus the gradient of phi dot d vector. It's the same thing, dv, plus the integral of the surface of rho d vector dot n hat. Sorry, phi. Yeah, this should be phi, my bad. dA. So what we can see here is that this front side here, this could be separated into two different integrals. So the first side is the integral of the divergence. And if you know about the Stokes law, this would be the same thing as the integral of the surface plus the surface prime, where surface prime is the outside here, of phi d vector dot n hat prime. N hat prime is the one for the surface here, so this is n hat prime. And going inside is also n hat prime dA minus the integral of the volume, well, plus of the E vector dot D vector. You could see why, because negative gradient phi is E vector dV plus the integral of the surface of phi d vector dot n hat dA, like so. Now, if you notice here that one of them is surface plus the surface prime, and the other one is just surface, and noticing that the n hat here are opposite directions, this would mean that you could simplify this into half times the integral of s prime phi d vector dot n hat prime dA plus the integral of the volume of E vector dot D vector dV. Now something to note here is that the one on the left side here, this s prime, if you try to evaluate this for very far fields, when r goes to infinity, phi should go towards 0. Well, it is dependent on 1 over r, the d vector is dependent on 1 over r squared, and the area, if you go bigger and bigger, this would depend on r squared. And this would cancel each other out, but there will still be the 1 over r. And when r goes to infinity, this entire thing would go to 0. Therefore, you can simplify this into the integral of the volume of E vector dot D vector over 2 dV. And this is what we call as the energy density from the electrostatic field. So you could also rewrite this as long as it's isotropic, that when d vector is epsilon E vector, this means that your energy density would be epsilon E squared over 2, or it's the same thing as d squared over 2 epsilon. So it turns out that this idea of energy density is applicable for almost every single thing. Compare that if you try to use the charge method. So it's a very useful idea to remember that E dot D over 2 is generally the case for your potential energy. So now let's go to the idea of the coefficient of potentials. And in here, we'll be focusing on the energy from the coefficient of potential. So if you remember previously, we defined the coefficient of potential to be phi I is equal to the sum of Pij Qj, where Pij is the coefficient of potential. So with this, we could define what is the potential energy. Straight away, by using our definitions, the potential energy would be half times the sum of the phi i's of Qi. And this would be the sum of Pij Qj for each of the j. Therefore, this could be written as half times the sum of I and j of Qi Pij Qj. So previously, I have already talked about the properties of Pij, but I haven't fully proven it. So let's go and try to prove it now. So to prove the first property, we should try to understand about if you try to add a very small change of Q. Let's say you want to add some charge towards your first conductor, let's say. So this would be du, and for the very small dq1, this would be the differential half times the sigma of the derivative of the qi pij qj with respect to the q1. So if there is no q1 on the multiplication, it's going to be 0. The derivative is going to be 0. So we can ignore about that case. But if we try to think about if both of them are 1s, this would mean that this would become the p11 q1 squared. So this would be 2 times q1 p11 if you take the first derivative with respect to q1. And what if you only have the qi to be the q1? So if qi is the q1, this would be q1 p, sorry, let's don't put the summation here. So this would be 2q1 p11 and qj p1j, because this is assuming that our I is 1, so summation that with respect to j. And also, if the j is the one that has 1, it's going to be qi pi1 summation that over I, and multiply this by dq1. So therefore, we could simplify this further into half times the sum of I of p1i plus pi1 times q1 dq1, sorry, qi. But if you also consider our very initial definition from the work when the potential is constant, if you try to add a very small charge q, it's like moving it from very far place towards that location. The u is just going to be q times the phi, right? Or in here, it's just q1 phi 1. And then if you take the definition from the coefficient of potential, this could be written as q1 of p1i qi, like so. And this is for the very small charge dq, like so. So now if you compare these two should be the same, because one of them shows you about the potential energy, but you only observe the initial and the final state, while the other one places a charge from very far towards your system. This means that they should be the same. And so if you take this similarity and try to observe, it turns out that P1i is Pi1, or in general, Pij is Pji. And it means that the matrix is symmetric. That's the first property of the coefficient of potential. The second property comes from if you try to assume that all of the charges are 0 except for Q1. So let's say you have a system and you have multiple conductors here. And you would have this guy to have charge Q1. And if this is positive, this would mean that it would radiate out the electric field, like so. And if you understand about the idea of potentials, Q1 should have the highest potential because it's the source of this electric field. So this would mean that your phi 1, which is the P11 times the Q1 here, it has to be greater than 0 because at a very far field, phi is going to be 0. So obviously your phi 1 should be higher than this 0. And this would mean that P11 must be greater than 0 because Q1 is greater than 0 as well. So what you see here is that if the entry is the same, the value should be greater than 0. But what about for the other potential? Let's say phi 2. This would be P12 Q1, well, P21. And Q1 is greater than 0. And the question is phi 2 greater than 0 or not? Now, if you assume that this is your Q2, and there's this electric field hitting this conductor, in order for it not to have any charge, it must radiate out the same amount of electric flux coming in. That's the idea from Maxwell's equation. So this means that it would radiate out as well. This would mean that phi 2 must also be greater than 0. But also phi 2 is less than phi 1 because as you can see here, that phi 1 is greater than phi 2 because of the electric field comes from the Q1. So this means that you could see that Pij must be greater than 0. That's the second property. The last property comes from this thing here, but we'll do this in a much more general case. Let's say if you give a wire towards, let's say Q3 or Q2, same thing. This would mean that their potential is the same, meaning that instead of phi 2 is less than phi 1, you could state that the phi I is less than equal to phi 1. Now, if you express this much more further, and assuming it's just Q1, this would mean that Pi1 must be less than equal to P11. Or in general, it's actually Pii is greater than equal to Pij. And this is the third property of the coefficient of potential. So this coefficient of potential method is a easier method for you to compute the potential at certain points as well as the energy, but you would need to know about the coefficient of potential first. So therefore, you need to do some experiments to figure out what's the coefficient of potential. Now let's go to the idea of the inverse of the coefficient of potential. This is called the coefficient of capacitance and inductance. So we will later see what these two actually mean. But if we try to observe the inverse of our problem, like phi I equals to Pij Qj, if we take the inverse problem, this would become Qi is equal to Cij phi j. Now doing the inverse will give you certain properties. First, Cij is still the same thing as Cji. Second of all, Cii is greater than 0, and this is what we call as the coefficient of capacitance. But if you know about linear algebra, if your matrices of them, if all of them are positive, the off diagonals have to be negative. So therefore, Cij is less than 0, and this is the coefficient of inductance. So now let's consider about the capacitor. So the capacitor is defined to be two different conductors with opposite charges which stores electrical energy. So if you define this by using the coefficient of potential, you could say that phi positive is P plus plus of the Q minus the P plus minus of the Q. And for the phi negative, this would be P negative positive of Q minus P negative negative of Q. So this is a property of the capacitor. So we can simplify this further. It's just P plus plus minus P plus minus of Q. And the other one is P negative positive minus P negative negative of Q. And what you can do is that you could try to figure out the difference between the top one and the bottom one. So the change of phi would be P plus 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 P negative negative minus 2 plus minus because these are symmetric, like so. So as you can see here, this is basically relating the potential difference as well as the charge that you have, and it is given by a certain constant. But we can make this much more simpler. And this constant here is normally defined to be 1 over c. So Q is C delta phi. And the C here is called as the capacitance. So from the equation that we have here, P positive positive and P positive negative, we know that this should be greater than 0. But the P negative positive minus P negative negative should be less than 0. And subtracting them both would give your capacitance to always be greater than 0. So it's a very unique property of the coefficient of potential that give us the capacitance to be greater than 0, always. And so for the electrical engineer out there, you might be asking about what's the unit of the capacitance. This is defined to be the coulombs over volt, or defined to be the farad. So I have mentioned about the capacitor being able to store energy. So what's the energy for the capacitor? Well, if you only just use the definition of the potential energy that we have already used, this would be half times the Q positive of the phi positive plus, well, we can just remove that, half times the negative Q phi negative. And therefore, the potential energy is just Q delta phi over 2. Or we can rewrite this as capacitance times delta phi squared over 2, or same thing as q squared over 2c. So maybe we could try to think about a certain example, and one of the most popular example for a capacitor is the parallel plate. So let's try to figure out what's the capacitance of this parallel plate. So maybe we have already charged this. So let's say we have this potential here to be phi positive and phi negative. So we would have like the delta phi here. And let's call this distance to be d. So therefore we could get the electric field. It's delta phi over d. And this electric field here could also be related to sigma over epsilon, where sigma is the surface charge density. So this would become Q over epsilon A. So now if we see here, we can actually get the relation of this capacitor again. It's Q equaling epsilon A over D of delta phi. And this is your capacitance for the parallel plate. So as you can see here, we transform a electrical quantity into a much more physical quantity. You have the area, the distance, as well as the property of the material. Now, for those who are taking electrical engineering courses, you might know that there are two different ways for you to hook up the capacitors. There is the parallel as well as the series. But technically, there are much more complicated configurations that you could do. But in here, I'll be discussing only about these two simple forms. So for the parallel plate, if you apply voltage, let's call this phi positive and phi negative here, you could combine this into one single capacitor with total charge, Q total, and it's defined to be this first charge and the second charge here combined, Q1 plus Q2. And this should be the capacitance times the delta phi. And the delta phi here is the same. So it's just the capacitance of the equivalent capacitance times the delta phi. And you could substitute this Q1 and Q2 to be C1 delta phi as well as C2 delta phi. This would mean that C1 plus C2 is C equivalent. So for a parallel configuration, you could just add up the capacitance in order to get your equivalent capacitance. For the series, if let's say this is phi positive and this is phi negative, there will be charge buildup here and negative charge buildup here. But also this would mean that for each capacitors, there would be an opposite charge on each of these, like so. So if this is capacitance 1, this is capacitance 2, our total change of phi, this would be the change of phi from the first one and the second one added up. So it's like Q over C1 and Q over C2. And this must equal to Q over the C equivalent. So if you see from this equation, the equivalent capacitance reciprocal is just the sum of the reciprocal of each of the capacitor, like so. So now you can see why the equivalent capacitance are defined to be so, because one of them is conserving the charge and the other is conserving your scalar potential difference. So finally, we are able to discuss about the force as well as the torque. So force and torque are actually quite similar. So you could define work to be F dx or also tau d theta. They are both the same thing. And now if you try to consider an isolated system, isolated meaning that the total energy is zero, or basically there's no energy going out or in, this would mean that all of your potential energy plus the work must always be a constant. So this would mean that the change of work plus the change of the potential energy must always be the same, which is zero. So therefore, this would obtain that your force is negative gradient u. Same thing for the tau. Tau is negative gradient u. But this doesn't work for a non-isolated system. Let's say if the voltage is kept constant. This is a typical example. So this would mean that you would be supplying a battery into your capacitor, something like so, and you're only looking at this system of capacitor. So, so if you try to sum up all of the changes, the change of the work plus the change of the internal energy would be the same as the change of the work from the battery going towards your system. So this would mean that your work plus potential energy is increasing. Your energy is increasing by applying this work from the battery. And so if you try to analyze what's the actual values, the dW here plus in here the du is half Q5 for each of the components must equal to the work of the battery. And in here, because we are keeping our potential to be constant, we could just use the definition of Q5. Well, technically it's dQ in here. So we can simplify this, and it turns out that du is half dq phi, or this is just the du. So what we can get from this is that the force is the gradient of u with constant potential. And same thing for the torque, it's just the gradient of for the theta of of the potential energy with constant potential. And for the top one, it's just constant charge. So the following simulation here shows you the two different scenarios. One of them is with constant charge, the other one is with constant potential. So I won't derive the exact force again, but I will show you what we got for the forces. The one with the constant charge has dq squared epsilon r minus 1 divided by 2 epsilon 0 work of epsilon r minus 1 times x plus L everything squared, like so. And for the constant potential, this is epsilon 0 delta phi squared of the width, divide this by the separation distance, multiply this by epsilon r minus 1. You would see that these two forces are always positive. But let me show you the difference between the constant charge and the constant potential. The first one is that for the constant charge, you could see here that the force is non-constant. Compare that to the constant potential. This one is constant force. So you might be asking, why is one of them non-constant and the other one is constant? And if I explain it by using potential energy, it might be less intuitive as where the force comes from. So let's instead try to think about what is happening when we have a parallel plate. If you have a parallel plate, and let's say the top side is positive and the bottom side is negative, and let's say you apply a dielectric in between here. Regardless if it is constant potential or constant charge, what you would notice is that in this side, sigma has to be greater compared to the sigma here. But this doesn't mean that the sigma will be negative, because if it's negative, the electric field will flip, and therefore the boundary condition within this small place here is not gonna be fulfilled. So therefore, we know that this other side here has to be a positive value as well. Meaning that if there is this positive charge here, and there's this electric field going to the bottom, there will be polarization on the dielectric. So there's the positive and negative here. And this positive negative induced dipole here is going to be attracted by this positive charge here, meaning that there is force that is going to push this plate much more in, or the attractive case. So that's the simple explanation as to why it is attractive. But the reason why the forces actually change comes from how you balance out the sigma. For the constant charge, you need to make sure that Q must always equal to sigma of the air of the area of the air plus the sigma of the dielectric times the area of the dielectric. Compare this to the one with the constant potential. The constant potential doesn't care if Q is conserved or not. It only cares that delta phi is the same, meaning that your electric field is always the same. And this would mean that your sigma on the air is always the same. So if you look at the simulation once again, what you would see is that for the one with the constant voltage, the surface charge density of the one with air is maintained to be the same. Compare that to the one with constant charge. It is decreasing. So the force will dwindle for the one with constant charge, and the one with constant potential would have this extra charges for it to pull the dielectric in. And so that's the intuitive explanation of why our simulation, of why our experiment has this type of force. And so that's all for today's video on electrostatic energy. So in the next video, we'll be discussing about one of the most important things in electrical engineering, which is the current. And so make sure to like and subscribe so that you don't skip that next video. And also please share this to your friends who wants to understand physics in a much more deeper level. Thank you very much, and I will see you on the next video.